The first time I met Dr. Rafael Santos, he was furious because the underwater drone I designed for deep-sea cable repair had malfunctioned at 2,800 meters depth, destroying 6 months of his oceanographic research equipment. My name is Connor Blake. I'm 27 years old. I design autonomous underwater vehicles for SubMarine Dynamics, and I've spent the last 4 years building robots that do jobs humans can't survive doing. Deep-sea environments are hostile, unforgiving, and entirely dependent on equipment that works perfectly. There's no margin for error at depths where pressure exceeds 4,000 pounds per square inch. Dr. Rafael Santos, 30, is an oceanographer researching deep ocean thermal vent ecosystems. He spent 3 years positioning specialized monitoring equipment at 2,800 meters depth near the mid-Atlantic ridge, collecting data on chemosynthetic organisms that might reveal how life originated on Earth. His research is groundbreaking, precise, and now destroyed because my autonomous underwater vehicle had a thruster malfunction. "Your robot crushed my entire sensor array," he said, standing in my lab at SubMarine Dynamics headquarters in San Diego, holding the mangled remains of what had been a $400,000 specialized camera system. 3 years of positioning work, 8 months of continuous data collection, gone. Because your AUV had a mechanical failure you didn't anticipate. The thruster failure was a manufacturing defect from the supplier, I replied, examining the damaged equipment. Not a design flaw in my system. I've already filed a claim with the manufacturer. Your equipment will be replaced. I don't want replacement equipment. He set down the mangled camera with controlled anger. I want equipment that doesn't get destroyed by your malfunctioning robots. I want you to understand that when you design systems for deep ocean work, people's careers depend on them, my career depends on them, and you sent a robot down with a known supplier issue. I didn't know about the supplier issue until the malfunction. Exactly, you didn't know. Which means your quality control process is inadequate. Which means you're putting researchers at risk. He turned to leave, then looked back. Fix your process before you send another AUV to the deep ocean. Because I'm not the only researcher who depends on your equipment working perfectly. He left my lab and I spent the rest of the day staring at the damaged sensor array, wondering if he was right. Was my quality control inadequate? Had I been overconfident in my designs? I assumed I'd never see him again. I was wrong. 4 months later, the cable rupture emergency. The call came through at 300 hours on a Thursday morning. A transatlantic telecommunications cable had ruptured at 3,200 meters depth, approximately 150 miles off the coast of Portugal. The rupture was in a critical junction point serving 6 European countries. Internet services were already failing across the continent. My company was being contracted to send an AUV to assess the damage and prepare for repair operations. This was the kind of mission that defined my career. High stakes, technically complex, dependent entirely on equipment that had to work perfectly. And I had to face the fact that Dr. Rafael Santos, who'd made it clear my quality control was inadequate, would probably hear about it. I was wrong about that assumption too. At 0400 hours, my operations director called me. "We have a researcher requesting to join the expedition, Dr. Rafael Santos from the Scripps Institution. He says he's been working on deep ocean environmental monitoring equipment, and he wants to observe the cable repair operation to validate some of his equipment designs for use in high-pressure environments." My stomach dropped. "Get him on the phone," I said. Rafael's voice was professional, businesslike, completely devoid of the anger from 4 months ago. I heard about the cable rupture. I also heard SubMarine Dynamics was being contracted for the repair AUV. "I want to observe the operation. My research requires equipment that functions at 3,000 plus meter depths. Watching your repair operation will help me understand failure modes and design solutions." "You hate my company," I said. "I'm disappointed by your quality control process," he corrected. "But I respect your engineering. Hating and respecting aren't mutually exclusive." He paused. "Are you willing to let me observe? Or is this too uncomfortable?" The research vessel. Day 1. The research vessel arrived at the cable rupture site after 3 days of transit. The weather was rough. Atlantic swells, wind gusts, and the kind of conditions that made deep-sea operations more dangerous than usual. Rafael arrived with 2 colleagues and several cases of equipment designed for high-pressure monitoring. I met him on deck and he looked different than in my lab, weathered by sun and salt, wearing tactical ocean research gear that showed he'd spent considerable time on research vessels. But his eyes were the same, intelligent, precise, and still slightly angry. The rupture is at 3,200 meters, I explained, pulling up the sonar data. Rough terrain, strong current at that depth, low visibility even with the AUV's lights. The cable shows shear damage on the western side, suggesting some kind of debris impact. We need to assess whether it's repairable, or if the cable section needs replacement. What's your AUV's depth rating? Rafael asked. 4,000 meters maximum. This rupture is well within operational parameters. And your failure analysis since the sensor array incident? Complete overhaul of the quality control process, new supplier vetting protocols, 3-stage verification testing before deployment. I've been paranoid about failure modes. I looked at him directly, because I understood your point. When equipment fails at depth, people's years of work disappear. I didn't want that to happen again. Rafael nodded. Good, then let's design the inspection protocol together. You understand the AUV capabilities, I understand deep ocean environmental factors. Between us, we'll get accurate data about what happened to the cable. The deployment, hour 6. The AUV descended from the surface in stages, stopping at depth intervals to allow systems to equilibrate with pressure. Rafael was in the operations center with me, watching real-time video feeds from the AUV's cameras, monitoring pressure sensors, tracking the descent profile. Pressure readings nominal, he observed, scanning the data. Your system design is sound. The pressure seals are working properly. I designed those seals after studying your equipment, I admitted. The way you'd positioned your sensors to maximize durability at depth. I borrowed some of your design philosophy. That's called learning from criticism, Rafael said. And I heard something underneath the professional tone. Respect, maybe even approval. The AUV reached the cable rupture site at 3,185 meters depth. What we saw on the camera feed was worse than anticipated. The cable wasn't just ruptured, it was crushed. The sheath was compressed. The internal structures collapsed, suggesting the cable had been caught in some kind of subsea landslide or debris fall. The western side of the rupture showed fresh breakage. The eastern side was buried under sediment and rocks. This isn't repairable, Rafael said immediately. The cable's internal structure is compromised. You can't fix that at depth. You'd need to replace the entire section. Replacement means severing both ends, retrieving the damaged section, and laying new cable, I said, calculating the scope. That's a 3-week operation minimum. 6 European countries without backbone internet service for 3 weeks. Or we accept the operational failure and work with what we have. Rafael pulled up data from his environmental monitoring equipment. But before we decide on replacement, we need to understand what caused the collapse. If it was a subsea slide, there might be continuing instability. If it was debris impact from a surface event, we need different mitigation strategies. How do we determine that? We send the AUV deeper. We survey the area around the rupture. We look for evidence of recent sediment movement, for debris patterns, for anything that shows us what happened. I looked at the operational parameters. That means 2 more hours of AUV operation. We're already at 85% of the mission duration I planned. Then we adjust the plan. Rafael met my eyes. That's what we do in oceanography. We plan, and then the ocean forces us to improvise. Your AUV is capable of this. I trust your engineering. Something in my chest relaxed. He was trusting me after I destroyed his equipment. After 4 months of silence, he was choosing to trust my systems when it mattered. Okay, I said, we extend the mission. The AUV surveyed the area around the cable rupture, moving slowly through the dark water, its lights illuminating only a small radius in the absolute blackness of the deep ocean. Rafael narrated what he was seeing: sediment patterns, rock distributions, the signature of recent geological activity. Recent subsea slide, he said quietly, watching the video feed. Look at the sediment disturbance patterns. This happened within the last 6 months. The rocks have sharp edges, not weathered. The sediment hasn't compacted. This was a recent event, which means there could be continuing instability, I said, understanding the implications. Which means we need to monitor this site for a week before we do replacement operations, The slide is stabilizing now, but if we start pulling on the cable, if we're removing sections of damaged material, we might trigger another event. Rafael pulled up his monitoring equipment data. I can position my sensors here. I can track seismic activity, sediment movement, anything that suggests the slope is becoming unstable again. For a week? For however long it takes to confirm the slide is stabilized. He looked at me. And I want to use your AUV for ongoing monitoring. If your quality control is truly improved, I want to validate it with continuous operations. That means daily AUV deployments for 7 days. Yes? That's going to be expensive. My institution will cover it, Rafael said. This is important research now. We're not just looking at a cable rupture. We're looking at active geological processes in the deep ocean. This is oceanography at its best, responding to unexpected conditions, gathering data, understanding what the ocean is telling us. I looked at him and I understood something I'd been too defensive to recognize 4 months ago. Rafael wasn't angry with me because my engineering was bad. He was angry because my engineering was responsible for people's work, and he cared deeply about that responsibility. He held me to a high standard because he believed I was capable of meeting it. For 7 days, we deployed the AUV continuously. Every morning, I prepared the vehicle for descent. Every evening, Rafael analyzed the data his sensors had collected. Every night, we sat together in the operations center, watching real-time feeds from the deep ocean, understanding the geological processes that were determining whether the cable replacement could proceed safely. On the 4th day, there was a minor seismic event, magnitude 2.3, barely noticeable at the surface, but tracked perfectly by Rafael's sensors at depth. The slope is adjusting, he said, watching the data. The slide is still stabilizing. We need to wait longer. On the 6th day, the seismic activity ceased completely. The sediment pattern stabilized. Rafael's sensors showed no movement. One more day, he said, just to be sure. On the 7th day, Rafael confirmed the slope was stable. The cable replacement could proceed. 6 European countries could get their internet back. And the deep ocean had taught us both something about respecting the forces we were working with. Your AUV performed perfectly, Rafael said as we prepared for the final descent to retrieve his monitoring sensors. Every deployment, every pressure reading, every sensor integration worked exactly as designed. You've done the work I suggested. You've improved your systems. Because you were right, I said. I was overconfident. I wasn't taking responsibility seriously enough. And now? Now I understand that every piece of equipment I design is supporting someone's career, someone's research, someone's contribution to human knowledge. That's responsibility I can't ignore. Rafael nodded. That's grown-up engineering. The return voyage took 3 days. The cable replacement team was already mobilizing, preparing for the operation that would restore connectivity to 6 nations. Rafael and I worked together on final data analysis, combining my AUV operational data with his environmental monitoring information to create a complete picture of what had happened to the cable. His 2 colleagues had returned to the research vessel's common areas. Rafael and I were alone in the operations center, comparing notes on a large monitor showing the subsea topography and the rupture location. Thank you, I said. For what? For giving me the opportunity to improve. For not just dismissing my company after the sensor array incident. For trusting my engineering when it mattered. I didn't forgive you, Rafael said carefully. I challenged you. There's a difference. I believed you were capable of doing better, and I wanted to see if you'd do the work. And you did. He looked at me. That's why I requested to join this expedition. Not because I wanted to observe your company, because I wanted to see if you'd actually listen to criticism and improve. And you did? I reached over, took his hand. I fell in love with you somewhere between the sensor array disaster and the cable rupture site. I know, Rafael said. I watched it happen. I watched you getting more thoughtful about systems design, more careful about quality control, more conscious of the responsibility your engineering carries. That's attractive. That's someone who's actually grown. So what now? Now we see if we can build something that lasts longer than a research expedition. Rafael moved to San Diego to continue his research and to work with me on a joint project. designing equipment that could function at extreme depths while supporting oceanographic research. We combined his expertise in deep ocean environmental monitoring with my expertise in autonomous vehicle design. The result was a new generation of AUVs designed specifically for scientific research, systems that prioritize data integrity, equipment protection, and environmental monitoring alongside structural reliability. This is the best work I've done, Rafael said, looking at the prototype, because I'm designing with someone who understands both the engineering and the responsibility. And I'm doing better engineering because I'm working with someone who understands what the equipment means to researchers, I replied. We started a consulting company together, SubMarine Scientific Systems, focused on designing equipment for deep ocean research. Rafael brought the oceanographic expertise. I brought the engineering expertise. Together we created systems that were more thoughtful, more careful, and ultimately more successful than anything either of us could have designed alone. Do you still think my quality control was inadequate? I asked one evening, as we were reviewing specifications for a new AUV model. Your quality control was inadequate 4 months ago, Rafael said. Your quality control is excellent now. That difference is because you learned from criticism instead of being defensive about it. That's maturity. I learned from you, I said. You learned because you chose to listen, he replied. That's all me. That's the choice you made. I pulled him close and we stood together looking at the prototype, a physical manifestation of two people learning to work together, learning to trust each other's expertise, learning that responsibility and love aren't separate things. They're expressions of the same commitment to care deeply about the work and about the person you're doing it with.